This is section 8.4, day 2 notes. Students will be able to solve improper integrals. Here we have evaluate 0 to 3 of 1 over x minus 3 to the 2/3. Well, we have this interior point at 1. That's the problem. That's going to make the denominator 0. We have to split this over 1. So we have the limit as a approaches 1 from the left, limit as b approaches 1 from the right. So we're going to go from 0 to a, and then b to 3. So we integrate, take the antiderivative, plug in a, plug in 0. So we have top is a, 0 minus 1 is negative 1. Now we're going to plug 3 in, and we're going to plug in b. But then we evaluate this at, 1 minus 1, that's 0. And over here, 1 minus 1, that becomes 0 right there. And then in the middle, you have negative 1 to the 1/3 is negative 1. So you end up with plus 3, third root of 2. Now that has some decimal value to it, but that doesn't matter unless it would be multiple choice. Infinite discontinuity at an endpoint. Well, the endpoint of 2 is the problem child there. That causes the denominator to be 0. So we're going to approach 2 from the left. The antiderivative is natural log of x plus 2. Plug in a, plug in 1. 1 minus 2 is negative 1. And then we have the natural log of 0 minus 0. But, the graph of natural log looks like this. And so this is headed, as x approaches 0, we're going down to negative infinity. So this one diverges. Test for convergence and divergence. When we cannot evaluate an improper integral directly, often the case in practice, we first try to determine whether it converges or diverges. If the integral diverges, that's the end of the story. If it converges, we can then use numerical methods to approximate this value. In such cases, the following theorem is useful. Now, what this theorem says is if you can show that f of x is always less than g of x, then let's say you have, g of x decreases very quickly. There's your g of x. And f of x is always below. Well, if g of x is decreasing fast enough and f of x is always below, then f of x must be converging as well. We can also say if f of x diverges, in other words, f of x is not decreasing fast enough, and g of x is always above, then g of x must diverge as well. And that's what this box kind of says. If let f and g be continuous on a to infinity with f of x less than g of x for all x, then f of x converges if g of x does. So f of x f of x converges if g of x converges. G of x, this one diverges if f of x diverges. Here's our example. Now this is, does the integral d of x converge? So we're looking at the integral of 1 to infinity of 1 over e to the x squared dx. Now we're going to compare that to the integral of 1 to infinity of, how about 1 over e to the x? Now, a bigger denominator means a smaller fraction. So we know that 1 over e to the x squared, how did that change to an eraser? 1 over e to the x squared is less than or equal to 1 over e to the x. A bigger denominator creates a smaller fraction. Well, now we just have to show that this converges, which means this will converge. So we're going to go limit as a approaches infinity, integral from 1 to a, of 1 over e to the x dx. So we have the limit as a approaches infinity. Now that's e to the negative x. So our antiderivative is negative e to the negative x from 1 to a. Limit as a approaches infinity of, let's go negative 1 over e to the a plus 1 over e. And we have, let's go with negative 1 over infinity, because e to infinity is infinity, plus 1 over e. So this converges to 1 over e. So now we can say by comparison test, the integral from 1 to infinity of e to the negative x squared dx, all we can say is that it converges. We can't say what it converges to, but we can say that it converges. Converges. I keep hitting the erase button on this pen. Next, guys, 31 to 34. Use the comparison test to determine whether the integral converges or diverges. So we're going to compare this to 1 over x to the third. And we can say, we got to say this statement right here. Now, limit as a approaches infinity, 1 to a, 1 over x to the third. That converges because we can say that p, the power, is equal to 3, which is greater than 1. So because this converges, we can say by comparison test, our original integral converges. Now this is not a comparison test. I don't have like a smooth transition to this one. I just thought this would be a tricky problem. Here we're going to let u equal the square root of s. So the derivative, remember s is to the 1/2 power. So the derivative is 1/2 s to the negative 1/2. Now we don't have a 1/2 square root of s. We just have 1 over square root of s. So we're going to multiply the 2 over. With u substitution, the ds over square root of s becomes du. Well, it becomes 2 du. So there's the 2 du. But here, if we take this line right here, we can say that u squared, if we square both sides, we can say that u squared is equal to s. And we end up with this right here. Now, the antiderivative of that is inverse tangent of u, which is square root of s. We have... We're plugging in a, and then we're plugging in infinity. So 2 inverse tangent of infinity, really. This square root of infinity is just like saying infinity. Because if you look at the square root graph, there's square root. So that's headed to infinity. Now this part is going to be 0. Inverse tangent of infinity is pi over 2. Pi over 2. And then multiply the 2's, or cancel out the 2's, and we get pi. Evaluate the integral and state that it diverges. Here we have the natural log of w. And in order to do this one, we look at the definition of absolute value is equal to, it stays the same for x greater than or equal to 0, and we do opposite of x for x less than 0. Which means when we're going from -1 to 0, those are negative values. So instead of having w there, we could put in negative w, because you're opposite of x when x is negative. But then instead of putting absolute value here, we can put in just w, because if you have absolute value of x, you can just write x for values greater than 0. Well, now we have to do the antiderivative of natural log. So we pick u as natural log. Take the derivative. dv is just dw, so v is w. And here is the antiderivative of that piece. And here's what we end up with right here. So that is the antiderivative. And then the antiderivative of the other piece with the positive just happens to be this one right here. We plug in the a, and then the a, we plug in the 1, plug in the 1, plug in the b, and you get lots of zeros. But this is 0 times negative infinity, so we end up using L'Hopital's. There's L'Hopital's to show that that actually goes to 0. Here's L'Hopital's over here to show that piece actually goes to 0 also. So you end up with -1 and -1, which ends up being -2. Use the comparison test to determine if the integral converges. We're going to compare this to 1 over x to the 4th, and we can make this statement right here. Now, I wrote it all out with work. And what we compare it to ends up converging to 1/3, so we can say by comparison test, this converges. But we could also say that right here, that p is equal to 4, which is greater than 1. So converges. Evaluate the limit using L'Hopital's. Our indeterminate form is 1 to infinity. We're going to let y equal the function. So the natural log of y is 1 over x natural log of e to the x plus x. We're going to use L'Hopital's. And we have, let's see, 1 over e to the x plus x times e to the x plus 1. That's the derivative of the inside. And it's over 1. The derivative of x is 1. So we plug 0 in, we end up with 2. So the answer ends up being e squared. Evaluate the improper integral. There's putting the limit in. There is the antiderivative. That's plugging in all of the values. But now, look at this. We have the square root. Well, we have a over the square root of 1 plus a squared. And then this right here, that piece is going to be 0. And then this piece is the natural log of the square root of 2, which ends up being in the top right here. Well, we could write square root of 2a squared for a squared of 2. We just end up putting the a in the radical, but you have to square it. Well, now we could have the square root of that whole thing, 2a squared over 1 plus a squared, and write it like this. So that square root is a 1/2 power. So that goes to being a 1/2 power. Now, taking the limit of this is like ending behavior. And 2a squared over a squared is 2. So we get the natural log of 2, and it ends up being natural log of the square root of 2.